first speaker today is going to be Stephen Diehl, well known for What I Wish I Knew When Learning Haskell and Write You a Haskell as well. I have another short announcement. Since a lot of people arrived today, we will allow another lightning session where people can introduce the projects they will work on after his talk. So if you're a project maintainer and you haven't advertised your project yesterday, you can take 2 minutes after the talk to do that now. So then I'd like to give the word to Stephen here.
Okay. Is this on? Okay, wonderful. Okay, so full disclosure, I made most of these slides about 24 hours ago. I'm particularly bad at public speaking, and yeah, I don't know how Jasper roped me into this talk, so now that the bar has been set kind of low, I'll jump into my talk. So I kind of copped out and basically did a bunch of slides about a project that I've been working on around the implementation of a bunch of cryptographic primitives that I've been working on for a company. So basically the entire premise of the talk is basically just going to be about all of the sort of Haskell machinery I needed to implement to actually build up a more complex construction that we're going to be building to do verifiable computing in crypto, which basically is involved offloading computations to untrusted parties and allowing them to run the computation with inputs and being able to detect any tampering. So to do that, we need quite a bit of cryptographic machinery. So I thought the best way to kind of jump into that would basically be to just derive some of the basic cryptographic primitives from first principles. So I put all of the code up on my GitHub. So if you go to Zuri Hack Crypto, you can see the kind of full expansion of the project, and you should be able to run stuff like the elliptic curve examples and just see how they actually work in practice. Okay, so the outline, I'm just going to go through a bit of abstract algebra, just enough to basically encode some basic ring groups, field structures in Haskell, talk about the basics of elliptic curves, how they work, the kind of 4 big cryptographic algorithms that fall out of elliptic curves, talk a little bit about homomorphic encryption, zero-knowledge proofs, non-interactive zero-knowledge proofs, and then discuss about the big construction, which is an implementation of a pairing cryptography library in Haskell, and it's used for creating verifiable computation with circuit compilers. So if you want to follow along, the Haskell code's all up there. Okay, so with any crypto talk, I have to put this slide. Don't actually use any of this code. I put it up on the GitHub basically for educational purposes. Implementing cryptography is extremely subtle. Generally, you want to pick the most stable, well-tested library that you know and just run with that. You don't want to do things like what I do in these examples, like use big num integers in Haskell. And you got to be wary about things like side channel attacks on your code, which basically means that for interactive protocols, you want to make sure that all of your code basically is completely deterministic, doesn't read from random addresses in memory, doesn't have secret branch conditions. You know, given as a function of the input, it's not going to allocate more memory based on the size of the inputs on the network. And more subtly, that the compiler is not going to actually introduce all of these things into your code. So generally, the big caveat is don't use things like integers in Haskell to implement crypto, even though they're rather convenient, and I use them quite frequently here. Don't use that in practice. So basically, you've been warned. Don't actually use those. Okay, so just a show of hands here, how many people actually know Haskell? Or, okay. So I'll put all the code example. Who here is familiar with like basic elliptic curve and cryptographic assumptions? Okay, so about a third-ish. Okay. So I'm just going to go through how we construct elliptic curves in Haskell. There are several well-known libraries that implement this a lot better than my simple examples do, namely things like Kryptonite. Is Vincent here in the room? Oh, yeah. Yeah, you should use his library for these things in practice, actually. So, but I'll just show you how to implement them very, very succinctly. So what is an elliptic curve? It's a family of equations relating 2 variables with a set of coefficients, a and b, such that they satisfy certain relations about the relationship between the coefficients. So the simplest kind of canonical example that everybody chooses first is these kind of short Weierstrass curves. They are equations of the form y squared is equal to x cubed plus ax plus b, where this relation between the coefficients hold. So elliptic curves have this wonderful property that between any 2 points, you can construct a tangent line, and that tangent line intersects with the curve at another point, as you can see in these illustrations up here. So that's going to give us a lot of very sort of rich algebraic structure that we can do to construct many things. Okay, so in order to kind of work up to building elliptic curve crypto, we need basic assumptions about what are groups. So a group is basically a set together with an operation that maps 2 elements to another element in the group. It's associative and has a neutral element with inverses. So the simplest like Haskell implementation would just be this type class with the multiplication function, the inverse, and then the unit. On top of that, there's a really, really important operation called group exponentiation, which basically takes a integer in the group element and then repeatedly applies the operation to the group element, producing sort of n-fold iterations on top of the multiplication operation. So, and then if the operation is commutative, if the group is called abelian. So importantly, in cryptography, we're generally going to be working with modular arithmetic. So the integers, which is represented by this big Z here, is a finite set of integers modulo some large prime number. If it's a prime, there's several interesting properties that fall out of the group structure that are really, really important, namely that the entire set can basically be generated by repeated applications of what's called a generator, by repeatedly applying the neutral element and then applying the multiplication operation to generate every element of the set. So I'm sure everybody's familiar with these finite fields where we have the set 0, 1, 2, and then we define our addition and multiplication operations to be just modulo the prime. So, okay, importantly, to calculate inverses for modular arithmetic, we need this extended Euclidean algorithm, which is well understood to produce inverses modulo the prime. So if I have an integer x and I take the multiplicative inverse modulo prime, x times the multiplicative inverse of x gives me back the neutral element. So this algorithm basically just recursively calculates that. So, and then we have rings, which consist of an abelian group with an extra operation plus that's associative and then distributes over the multiplication operation of the group. So in order to construct the rings that we're going to use for elliptic curves, we implement this basically as this ring new type over an integer, and then implement all of the arithmetic operations such that they perform the operations modulo p. So that's all this is. And then there's fields, which basically build on top of the groups, the rings, and the group structure to give us addition, multiplication, negation, inversion, units, and a 0, and such that we have the existence of, for every element A, there's a multiplicative inverse such that multiplying it by the inverse gives you back the unit. Okay, so back to elliptic curves. It turns out that there's actually a rather convenient group structure that falls out of elliptic curve point addition. So like I said before, if we consider the abstract notion of addition to be points on a curve, we can define addition to be given a point P and a point Q. The addition of those 2 points is a point R, which also lies on the curve, given that tangent line construction I spoke about before. And then we extend this point system with a 0 element, which is the point at infinity that ends at all lines parallel to the y-axis. And then we have these 3 relationships between those 3 points. So it turns out this is actually a group on top of the elliptic curve. It gives us a lot of nice properties. So In practice for these points, though, we might often switch back and forth between two different representations of the point. So the simplest one is just the xy affine coordinate, which is just the two x and y per the elliptic curve. So plugging in x, you get a y. And then we have the projective coordinates, in which we represent the 2D point as a 3-tuple, where the z is defined to be this denominator in this mapping between the 2 points. There are often benefits between switching back and forth between these coordinate systems because the point addition and multiplication operations with the projective coordinates sometimes don't have to do division, which is normally expensive. And so you don't have to do sometimes branching conditions that can produce code that runs in non-deterministic space. So, okay, so now we can just define, given our affine point, all of our basic arithmetic over the curve points. So here's an illustration illustrating the point exponentiation calculation, whereby I take a base point p, and by repeated application of multiplication by a fixed exponent, we get another point on the curve. So this is all in the real numbers, by the way. So the curve is defined over the reals. The doubling operation, these were all sort of well understood formulas for adding the points on elliptic curves. And then the multiplication operation, which is crucial to what we're doing here, where we take a point, a fixed integral value a, and if it's 0, we get infinity point, the point at infinity back. If it's 1, we get the point back. And if it's even or odd, we go to one of these branches in the code. So it turns out this is actually exactly the same as the group exponentiation operation I mentioned right here. And this is an operation that's very, very easy to do in one direction, but very, very hard to reverse. Okay, so those were curves over the reals. So now that we have all this algebraic machinery, we can basically consider the case where we're going to define the curve not over the real numbers, but over a finite field, namely a finite field where we take the integers modulo some prime number. So this is actually a curve, not quite the same kind of smooth curve you get in the real numbers, but it's there's a symmetry to it if you kind of stare about the x-axis here. That surprisingly enough actually has the exact same point addition and point at infinity group structure that the curve over the real has. And so at the bottom here, I've expanded out all of the integer powers of a single point, and you can see the distribution of points is seemingly very chaotic. There's actually some structure to it, but it's very, very difficult to go from these coordinates on here on the right back to recover the exponent on the left. So, okay. So to canonize that, this is known as the elliptic curve discrete logarithm problem. So given a b and a generator g in the group, given a, it's very, very difficult to compute the g of a that equals b. So this is widely believed not to be efficiently computable so long as you construct your fields and your groups in ways such that you don't have pathological curves or pathological fields. Just kind of give you an example of like the kind of order of these curves. There's a common set of coefficients for an elliptic curve called SCCP256K1 that's widely used. The order of that group is roughly 1 order of magnitude less than the number of atoms in the universe. So these are ridiculously, it fits on a screen, but if you were to enumerate from 0 to that number, it would take more time than the universe has been around. So that's the kind of scale about why these things are difficult to compute. Okay, so for the next couple slides, I'm just going to introduce some symbology. So P is going to be the, so there are many different elliptic curves that we can choose from. Given the choice of the underlying prime that we're taking the field to be modulo to, as well as the coefficients A and B, and then the generator point that we use to produce all points on the curve. So there are many sort of widely used, widely studied curves, but Curve 25519 is very popular. And then, so the P will be the prime field, A and B are the two coefficients in the elliptic curve equation, and G is the generator base point. And then N is the order of the group, which is the number of elements. If you're interested in how all the formulas that I put on the slide before were derived, there's a nice hyperelliptic.org that you can kind of see what the equations are, these in all of the coordinate systems. Okay, so what are the traditional uses of elliptic curve cryptography? It's used to power the internet. SSL uses this to do secure exchange of information. Elliptic curves admit the same kind of Diffie-Hellman construction, whereby two untrusted parties can, by exchange of their public keys, create a shared secret that can be shared in the clear and used to encrypt information. There's also an ECDSA algorithm, which is a digital signature algorithm, which, given a elliptic curve private key, we can produce a signature that, without repudiation, allows me to uniquely identify a message or a hash of a message as coming from the owner of my private key. And then verifiable computation, which is what I'll talk about today, which is basically the problem where we want to exchange information between untrusted parties and allow them to perform computation over that information in a way that either obfuscates the data or produces a sort of tamper-proof computation. And so we use elliptic curves for those. Okay, so the three kind of primitives that I'll talk about for building these kind of systems are commitment schemes, partial homomorphic encryption, and then zero-knowledge protocols. So in the slide here, there's a homomorphic repo, there's a pairing repo, there's a Sigma protocol repo, and then there's a zero-knowledge proof compiler. If you're interested in the full implementation. Okay, so the simplest kind of tool that we're going to use elliptic curves for is basically doing a commitment scheme. So if you consider the case where we have two parties, Alice and Bob, and they both want to engage in, say, betting on the result of a coin flip. They want to do this over the phone, say, or over a network protocol. The simplest case is where Alice and Bob are basically just going to place a bet in clear text and say, I say that it's going to be heads. And then Alice flips the coin and then says, okay, Bob, I got a heads. So this is problematic because, of course, if they're not trusted parties, any one of them can basically just change their result. I said, okay, it's whatever I said it was. So we need basically to tie their specific vote to a computationally irreversible problem, such that they cannot refute that they claimed that I claimed that this result was going to be heads. They can't change their vote, and they can have the option to reveal what their vote was after the coin toss in a way that no party can actually back out of this engagement. So these are well understood problems. They're called commitment schemes. So there's a particularly simple commitment scheme that is called the elliptic curve Pedersen commitments. So I'm using actually Vincent's Kryptonite library here instead of using the custom elliptic curve stuff. So basically this point basemal function right here basically multiplies a point by the generator of this SECP256K1 curve. So the commitment, basically both parties are going to agree on an A, and then Bob is going to commit to an X, which produces this commitment, which can then be shared with Alice, and then Alice will do the same thing on her end, commit to a specific value, and then they both share the specific X that they use to produce the commitment with each other, producing the plain text that both of them can agree on was the result that they put in sort of cryptographic lockbox after before the vote, and then they can reveal that to each other to expose the real values. So these commitments are also additively homomorphic, meaning that you have two commitments, you can combine them together in a way such that the underlying cryptotext can be added as cryptotext, which is quite useful for combining commitments together into more complex commitments. But that's this. The implementation basically just puts the commitment factor inside of the exponent of this base point, and then produces a bit of randomness, R, which is then added to the commitment, the base point, and then it combines and multiplies them. And at the end, that basically the commitment is basically, the randomness is basically removed as soon as the value is shared. So, okay. So then that's kind of the dumbest kind of how do we exchange a binary value between two parties. So there's a little more complex schemes where we want to do sort of computation over encrypted data. So there are schemes that allow us to do very, very limited sets of arithmetic computation over encrypted data. So these schemes basically allow either addition or multiplication or some limited addition and multiplication by constants to be performed over cryptotext, which allows basically two parties to particularly offload a value to an untrusted party, allow them to perform some computation over it, and then return it back to the original party, then decrypt it with the result of the computation applied on the underlying value. So these are useful in some cases where you have guarantees about the intents of the counterparties. So if they're not overtly malicious, these kind of schemes can work. And the biggest drawback of this, these kind of protocols is that they're malleable, which means that an untrusted party can perhaps perform the wrong computation over the result, and there's no guarantee that the integrity of the underlying data is preserved. So this is basically useful in a limited set of cases, but there's an implementation of what's called the Palio Cryptosystem, which is actually quite simple. It fits on this slide, which allows addition, homomorphic addition, and homomorphic multiplication by scalars over the cryptotext. There are proofs of construction about full homomorphic systems. So in the case where you would want to bed not just one arithmetic operation, but an arbitrary number of arithmetic operations, but they're not particularly feasible at the moment. There's a very influential paper by Gentry in 2007 that proved that these things can be constructed, but they're wildly exponential. Okay, so then the third construction that's a bit more useful is if we toss out the notion of I want to offload and obscure all information, can we construct something that's still useful in which counterparties can agree on a system in which they can perform computation, but without sharing the results with the counterparties in a way that they give a proof that they have performed the computation over the private data in a way that preserves the integrity of the computation that both parties agree on. So these are called zero-knowledge proofs. It's effectively a way by which a party called the prover can prove to another party, the verifier, the given statement is true without conveying information apart from the fact that the statement is indeed true. So the dumbest kind of example that everybody starts with is Alice wants to prove to Bob that she knows the specific x given a y that is the solution or the discrete logarithm of e to the x. So both Alice and Bob agree on the base point g. And then they go through this interactive protocol, which I outlined here, by which they obfuscate the chosen value by encoding it in the exponent of these two elliptic curve points, or the two elliptic curve generators. They send that information, choose a set of randomness, where this is this r and this x, that they exchange. They combine them together into this other value z, which is then exchanged, and then the verifier can check whether the relation between the two randomness and the scheme that they agreed on matches. So these are interactive proofs in the sense that both Alice and Bob need to exchange two pieces of information along with the setup in order to convince each other that they to complete the whole proof sequence. So these are not terribly useful in practice. Often what we want to do is basically just have a single proof term that can be sent over a network that conveys completely that Alice does indeed actually have the discrete logarithm solution to this. So there's a well-known transformation called the Fiat-Shamir transformation, which takes a interactive zero-knowledge proof and transforms it into a non-interactive zero-knowledge proof. Basically, by computing, instead of working with the field elements themselves, we work with the hash of the elements. So there's an assumption here is the existence of a function, which is a hash function, which maps every element in the domain A to a unique element in the domain B. And this model depends on the random oracle model, which assumes the existence of these functions. Whether or not these things actually exist is somewhat sort of a dodgy assumption, but in practice, like things like SHA-256 can be sort of computationally good enough that we can use them. So it's the same proof sequence for the non-interactive version, except that the information that Alice packs into the payload that she sends to Bob basically involves the hash of the base point, the output of the exponentiation, and then the random blinding factor. And the hash function is required to be not reversible, so it is interactively difficult to come up with the pre-image of this hash function. And then they proceed to basically compute the verification of those elements in a way that only requires one back and forth. So these are quite useful. What does this look like in Haskell? It's actually quite simple. So here, Alice is going to convince Bob that she does, in fact, indeed actually have a solution to this equation that produces this point, this public point, 115, 3479, and that answer is actually 42. So multiplying the base point of this curve by, or raising that base point to the 42 actually gives this point. But Alice is not going to actually share the number 42 with Bob, but she's going to convince Bob that she actually does have that number. And the sigma proof that, or the zero knowledge proof that Alice and Bob is going to exchange in the non-interactive form is about 10 lines of Haskell. But the most important thing here is that the secret value A is not actually shared over the network. It's completely obfuscated in the protocol. So Alice will send the proof over to Bob and then plug it into this verify function, which will subtract off the, which will verify the integrity of the proof. And if you run the example code that I spent, you'll see that's true, without actually sharing the secret key. Okay, so the dumbest case is where basically Alice and Bob just want to express that they have a solution to a discrete logarithm problem, but you can actually extend these protocols in a very, very general way by running them over multiple variables, by embedding multiple secret values in multiple discrete logarithm problems and arithmetic relations between the variables. So doing this, you can basically express an arbitrary number of simple arithmetic relationships between a set of secret variables things like quality, addition, multiplication, and you can also extend it to Booleans by basically running the protocol such that you accept the proof if any one of the given proofs fails or require that both of them fail. So this has to be agreed on beforehand, but you can embed fairly complex arithmetic inside of these things. The only downside to these things is they tend to grow quite linearly. So if you wanted to embed, say, that I have a specific, if I have 10,000 discrete logarithm problems that I want to choose, and I want to take the conjunction over all of them, this would end up becoming a very, very, very big proof to share over the network. So more recently, around 2013 actually, people have, there's a paper called by Arno and Brian that showed basically a way of doing the general form of this in a way that we can produce succinct proofs about arbitrary computation, not just arithmetic relations, in a way such that Alice and Bob can compile a effectively arbitrary program into a circuit whose output is a single proof that the circuit was run correctly for a given set of private inputs. So that's really kind of a non-trivial result. It's effectively that you can take an arbitrary program, compile it into a circuit, and then given a specific set of inputs, compute a proof that the result was run completely correctly, and it compiles into basically a single number that embodies the entire truth of that statement, which is a rather cool result. So over the last couple months, I've been working on basically a Haskell implementation of this compiler. I put a sort of limited version of it up on our website. I'm going to publish a bit more of it as soon as it's kind of polished and vetted, but I'm going to sketch out all the machinery we basically need to basically implement this paper in Haskell and show how it actually can be made fairly efficient. But we do need a bit of more machinery to actually implement this. So namely, we need an implementation of something called pairing cryptography. So there currently isn't a good crypto library in Haskell. So I've been working on implementing one, which I'm going to sketch out how you would implement that. There's a fair bit of sort of non-trivial things involved in this. So there's going to be a lot of equations. Most of them are fairly well understood instructions that depend on a lot of just parameters. So what is pairing cryptography? Basically, it's concerned with the construction of these mappings, E, that map between two different groups such that we can construct a bilinear mapping that has this relationship right here. And so the unique thing about this construction is that we're going to map between two different groups, one in which a specific variant of the elliptic curve discrete logarithm problem, so we call it the decisional Diffie-Hellman problem. So given two exponentiations by generators, consider whether they're equal, and then the computational Diffie-Hellman problem. What? On the third one here. E to the GB equal G equals HB?
You've got what? You've got E to the G and G.
Yes, sorry. Fine. But I guess, okay, so you're you're mapping between these two groups, and the mapping is going to let you do something rather interesting, which is given any kind of arbitrary exponentiation over the generators, we can move that exponent outside of the mapping, which is really, really important for producing sort of one-way functions between these. So to build on the kind of group structure that we were building on before, we're going to take sort of the base fields, which are these finite fields modulo prime, and construct what are called quadratic extension fields out of them, which are, you can think of the field as a set of elements with a single element on the right-hand side. And then we're going to extend that field by considering all linear combinations A plus UB, where U is a element that behaves like the imaginary number I, such that it squares to -1. So it turns out we can construct a tower of these quadratic extension fields on top of each other, such that we get a very, very large set of equations about that are, we construct these quadratic extension fields in such a way that certain arithmetic operations in the FQ12 field, when you do squaring over them, they tend to be just the reversing of a single sign. So that's really, really beneficial for an algorithm that depends on doing a lot of tens of thousands of these operations on them. So that's why that construction exists. So then the curves that we're going to be choosing are what are called Breton-Herrick curves. They're defined by generating these two field moduluses, Q and R, given as inputs to the Q and T equations, with this specific input called the Breton-Herrick input parameter, which is this T, is a prime. And then the choice of a coefficient for the quadratic extension fields, beta and xi, to be 9 plus u. So, these numbers look like pull out of nowhere, but there's actually like a derivation of them, why they exist in this paper, optimal implementation of the 8 pairing over Breton. So if you want to understand the exact reasons why these were chosen, that's there. And then we have this group selection. So the 2 generators for this Breton-Herrick group that we're going to be using are these 2 generators. And there's also a set of mappings for going from points in the base field, FQ, all the way up from FQ2 to FQ6 to FQ12 by these what are called sextic twist mappings. Read the paper if you're interested in those. So what does this actually look like in Haskell? So it's actually rather quite simple. We define a new type, which is basically the ring structure that we had before, and then we define the quadratic extension field to be the 2 coefficients multiplied by the scalar and then the plus u constant in the quadratic extension field. And then for FQ6, we have actually 3 elements, since the extension is a cubic order. And then in FQ12, we have just 2 elements again. But these are all building on top of each other to basically produce this tower field of quadratic extensions. So if you're interested in this one, the formulas for all of the arithmetic operations over these are expanded out. So basically we end up implementing num at the end of the day for all of these new types, which basically just offloads all of the addition, multiplication, squaring, and division operations to very, very long formulas that involve basically just expanding out the polynomial form of these quadratic extension fields. Okay, and then at the end of the day, we still want to construct this bilinear mapping between the 2 group elements. So there's a well-understood algorithm from algebraic geometry outlined in Boucher 2010, search for that paper, which gives us a way of constructing, given any 2 group elements, to construct the bilinear mapping between them. So at the heart of this algorithm is what's called the Miller loop. which is a recursive relationship between a specific mapping on the group to itself that can be iterated over again to produce this bilinear mapping. I'm not going to sketch out why this works. It does, and it depends on this binary expansion of what's called the Frobenius trace of the group selection. And then you run this iterative algorithm. I'll just show you it in Haskell, actually. It looks something like this, nothing really terrible. It's just basically just an iterative loop computing a lot of tangents and then squaring it at the end. The only thing is that this will typically involve like millions and millions and millions of addition and multiplication operations over the quadratic field elements, which typically tend to be extremely expensive because they're not mapping to a single CPU instruction. They're instead having to offload to this big num library, which is going to have to do millions and millions of these composite operations. So it's really, really important to actually optimize this. So a proper implementation of the pairing or the Miller loop has to be particularly optimal, and that's why this specific set of quadratic field towers was chosen, because there's certain properties of the field in FQ12 such that certain addition and multiplication operations basically just become flipping a sign, which ends up shaving off like 3/4 of the computations that you actually have to do to compute the Miller loop. And then at the end of the result, you basically do what's called this final exponentiation option, in which we raise the result of the Miller loop to q to the k minus 1 over r. K is this embedding degree of our field, which produces this unimaginably large number, at which you then have to exponentiate the results of the Miller loop by. And then you finally get this 8 pairing, which gives you the bilinear map that you want. So it actually turns out that when you're doing this Miller loop computation, there's a lot of computations that you can actually throw out or that are not actually necessary to perform. So actually, depending on Haskell's laziness, it's actually beneficial, surprisingly enough. And then at the end of the day, you get this mapping between the two groups, which you can then. So at the end of the day, this pairing is going to give us specific mapping into two groups, which you're going to use to compile these circuits. So the construction is basically, given an arbitrary lambda calculus program, or non-recursive lambda calculus program, we can take it and then transform it into a circuit, which can then be turned into a set of polynomial equations, which completely embody all of the inputs and outputs to the circuit. And it turns out that you can actually express any kind of arbitrary logic gate as combinations of the field elements. So the mapping between and, not, and, or's, or, there. So in fact, all of the circuits can actually be expressed in terms of just addition and multiplication operations over the field elements, where these are elements of the FQ12 field that we just constructed. And then inputs that are binary or numbers can be expanded out into binary forms, where each of the inputs to the circuit is a single wire that contains a binary digit. Then you can construct add and multiplication in the usual kind of circuit way by just basically adding the binary representation of the numbers. So as an example, if you have a circuit, which is basically the equation C1 plus C2 times C3 times C4. I'm going to construct a sort of obfuscated circuit out of this simple program. And the C1, C2, C3, C4 are all going to be private inputs to the circuit that we're going to compile and produce a proof that we did indeed, in fact, run this simple to we ran it correctly. To do this, we basically iterate through each element in the circuit. And then for every multiplication gate, we select a specific root and construct this sort of synthetic polynomial such that whenever one of the roots is 0, it implies that this other polynomial, which we constructed as the product of the left input circuits and the right input circuits, is always going to be 0 when the given root is 0. Paper is quite clear. But this is basically just an iterative walking over this large Haskell ADT to produce basically a list of ones and zeros about what the inputs and outputs and left wires and right wires of the circuit are. Okay, so then given those 3 polynomials, which are V, W, and Y, which completely define the entire circuit, we can then combine that with our choice of group to produce a encryption key, which is the polynomials evaluated at a secret point S, which is a random number chosen between 0 and the field modulus. And then we raise each of the polynomials for the circuit evaluated at that single point to the group element, and then we produce the 4 tuple, which is the encryption key, and then we produce a verification key, which is the polynomial for the D that we constructed in the last slide, raised to the group generator. And then the verifier, the person who's actually going to run the circuit and produce the proof that they did indeed run it correctly, is going to, given their specific inputs, evaluate the product of all of their encryption keys they're given, raised to the specific ith input of that circuit to produce the result of running that circuit over the specific input. And then the execution or the verifier, the prover, is going to compute via polynomial interpolation another polynomial over a free variable z, such that h of z, d of z is equal to v. The right-hand side is the polynomials that embody the circuit. And then this is the most expensive computation in this algorithm. So Lagrange interpolation is not cheap. And if you have a circuit with 50,000 gates, you end up with this polynomial of 50,000 degrees, which is non-trivial to compute, but it can be done efficiently. And then that's raised to the group element. And then the proof itself is then just the output of those last 4 results. And then to verify that the proof is actually correct, this is where we use the pairing machinery that we built before. We compute the mapping between G to the V of S to G to the W of S, and then divide by the pairing of G to the Y of S, and then just the base group. And we compare whether that equals H of S. So this equation right here is basically just the result of applying the bilinear pairing to the equation right here, such that the exponentiations for the negative terms become divisions. And then you get a single division of a element in FQ12, divide that by another element in FQ12, and then compare whether the two are equal. So at the end of the day, this entire basically proof that this entire enormous circuit of arbitrary size can basically be compiled down to a single proof that 2 elements in our FQ12 extension field are equal, which is a very, very small succinct proof, which is non-trivial actually. So if you were to implement this in Haskell, you basically end up with a small little domain language in which you have sort of enough machinery to say, like, if you wanted to construct a circuit that embodied like say, the knowledge that I have a specific pre-image to a hash function, you could compile a basic circuit of this form where you have a term language, and then you compile it into a specific set of gate operations where the primitives in Haskell are mapped through this bits type class down to their specific gate representation. So the circuit that I showed on the last slide that we computed the polynomials for is basically given by this equation. So it's rather trivial to take a sort of small embedded domain-specific language inside of Haskell, and then via this mapping and this pairing machinery, compile it down into this gate representation, of which you can then produce a single proof that the evaluation of it on an arbitrary computer by an untrusted party is actually correct. Is the end result, what we wanted to do, actually. So caveats of why this is complex is that it requires a lot of machinery to actually work up to the point where you can actually compile this circuit. The pairing machinery is non-trivial to implement. It's even more non-trivial to implement efficiently. The one that I put up in the GitHub is not as optimal as it could be. It works, but it takes about 4 to 5 seconds for a pairing, which is not particularly good. There are sort of C++ libraries that can do it in a couple milliseconds. But I'm sure we could get there at some point. And then, of course, like this paper basically just came out in 2013, so it's basically a very, very new cryptographic technique. It depends on the random oracle model. It also depends on this knowledge of exponent assumption that you can read in the paper, which is sort of not part of the standard model of cryptography. And then the generator of the verification and the encryption key needs to be a trusted party. So whoever generates the specific verification and encryption key for the specific circuit needs to not be a malicious actor in the system. The circuit compilation time for a very, very large program, like say an implementation of like SHA-256 compiled into a representation of gates is actually non-trivial. Involves millions and millions of these gates. You can do it, but it is an upfront one-time cost though. The interpolation function that the verifier has to do is actually, or the prover has to do is expensive. And then even when you're evaluating this, and you're plugging in specific, say, byte string into the hash function, there's a non-trivial overhead basically just to evaluating a single gate in the circuit, which is, which would be one CPU operation on, on a base or just default implementation in this cryptographic circuit. You end up doing hundreds of thousands of computations basically just to add 2 numbers, which is expensive. Proof, however, is quite short. It can be shared over the network, can be compressed down to 500, 600 bytes. And then the verification is relatively cheap at the end. So the complete verification that the circuit was actually executed correctly is only 3 pairing operations, which, all things considered, is actually quite cheap. So that's basically the entire construction. I put all of the machinery up on the GitHub. If you're interested in kind of hacking on this kind of stuff with me, I'll probably have a room somewhere later. I should warn again that this is very, very beta code. You shouldn't actually use it in production, but it is an implementation of something that we did actually need in Haskell. So feel free to look at it and run with it. And I guess that's it.
Some questions,
Sure.
Okay.
So long as it's not too complex.
More questions, if there are any?
Yes.
Yeah, how do you actually test your implementation? Because the reason I ask is someone shared a long time ago an RSA implementation in Haskell, and it worked against itself, but when I tested it against OpenSSL, it clearly didn't implement RSA.
Yeah. So the nice part about this specific construction is that there is actually several other implementations of it. So if you fix all of those kind of random variables that are put into the circuit, you can test that, say, all of the arithmetic over the quadratic extension fields matches the reference implementations. There are about 3 other implementations of them. They're all in C++. I would say they're not particularly readable or understandable, and I spent quite a bit of time reverse engineering them to build it in Haskell. As far as whether the circuit compiler is correct, there are, you can test the inputs and the outputs of the circuit, and if it gives the right inputs given, or right outputs given the right inputs, then it's correct. And if the proof verifies given a wide variety of inputs, you have a strong degree of faith in the implementation. But it's a big question. There's not a whole lot of. It's not like there's a SHA function or something where there's a large collection of input test vectors that I can feed through the system. But I'll say that all of the finite field machinery I've tested against the optimal 8-pairing library in C, and it seems to match in all use cases. In fact, I actually have a much stronger guarantee about the Haskell code because I can quick check it, which means I can enumerate vast quantities of test cases, and it seems to always hold the algebraic properties that I think it should. So.
You mentioned at one point that laziness was an advantage.
Yes.
Was it only at that point that laziness was, or was it an advantage throughout?
It's always an advantage. The only advantage I had with the laziness is in the Miller loop, which is this, basically this big for loop here, where I'm iterating over this unimaginably large number. So it turns out you can actually toss out quite a bit of the computations in this. So when it enters a specific branch, oftentimes this z to the I thing is a 0, or this ri. In that case, then you don't actually need to compute all these values. Is it beneficial outside of that? No. I think most of the modules actually have strict enabled by default. There's pros and cons to laziness. Useful to kind of be able to twiddle between the two when I need to. Yeah.
Hey, so you had this long list of requirements for cryptocode in practice, and you said your code doesn't do it, and then at the end you said that your code, you're using it in production or for something serious. So do you not care about these problems, or not yet? And how do you fix these problems in general in Haskell?
Is it this one that you're talking about?
No, on the very beginning, the one with the crypto warning.
The crypto one. So like the warning about crypto? Don't roll your own crypto kind of thing?
No, that next one.
Next one.
With the yellow sign.
Caveats, yes. Yeah, there's for the use case that I was intentionally designing crypto is this big suite of algorithms and techniques, right? And particularly the use case that I'm looking at is for completely non-interactive protocols. So there's not a big concern about like side channel attacks. So I can get away with doing things like using the big num library and that kind of sorts. But if you were implementing, say an SSL library, you would, since it's an interactive protocol, you would want to make sure that your code doesn't have any kind of secret branching and these kind of things. So, yeah, the concerns, this is just the general warning about crypto, but it's going to depend on what you're using it for. Don't rely on this code just yet, by the way. That's sad, but.
I had 2 questions actually, or one was an observation, I guess. Question. So have you looked at any just the circuit optimization things that people tend to apply to these things in practice when you SAT?
Yeah.
I didn't see if applied in your.
So could you basically have an operation that took gate to gate that eliminated a bunch of operations that were not necessary?
Like Chi-10 transformation.
Yeah. So that would be the next step. So some of the more robust implementations of that paper basically do just that, where they have, you can eliminate redundant gates and do optimization.
Yeah, I was just realizing that I could probably take most of the machinery that's inside of ersatz, which is a sat solver binding that I wrote in Haskell, and almost everything that we have that transforms our bit calculations and make those more efficient, like all the observable sharing, et cetera, would directly apply to your intermediate states.
Yep.
And then the other one was, there's a paper, I think it was last year, authenticated data structures generically. It was they do more of a Merkle hash style construction. So they're not blinding the data that they're sending to the server, but they're verifying that the server actually did what it said what it was doing with the data. Merkle tree construction. I don't know if you've seen this paper. I'll send you a link afterwards. But it seems very relevant to your interests.
Authenticated data structures.
But more importantly, it does not require that you give up recursion. So if you need to be able to move into this larger world and you're willing to unblind some of your data, this seems to be a thing that would fit with your needs.
So the answer to whether you can handle recursion in the circuit is that you would have to basically take your loops and
here you can't.
all of them.
Here you clearly can't.
Yeah. You have to have finite computation.
Here you're limited to circuits of polylogarithmic depth. It's a standard problem in fully homomorphic.
Yep.
But yes. Okay, thank you.
Hey, do you think it would be possible or feasible to compile a subset of the Haskell language to such a circuit? I think that would be pretty cool.
Subset of the Haskell language. Yes, the overhead of compiling it would be non-trivial. But I mean, not that bad actually. I mean, so long as, you're talking about like a strict subset, always terminating, all recursion bounds are known, simple flattened lambda calculus where I do all of the expansion of all subterms out. Yeah, you could do that. I would start with something probably like system F, untyped lambda calculus, kind of these kind of things first, but yeah, you could do it. Obviously, like for non-trivial programs, the circuit's going to grow very, very, very large. So you kind of want to have these kind of small kernels. But
yeah, could you comment on the economics of applying such a protocol? Because I imagine if the computation is very simple, the overhead of verifying and so on is not worth it. But at some point, it has to be worth it to do it. Is there kind of a theoretical limit for that?
Economics of it. Well, I'll say that it's not insanely expensive to do these kind of computations for, say, like you can compile like a SHA-3 circuit, and it's actually reasonable. It runs in sub-second time to actually compute the circuit as well, even though it has tens of thousands of gates. So the nice thing about this protocol is that the circuit compilation itself can be done up front. It's a one-time cost, and then it's shared with all participants. It can be quite large in practice, but not, you're talking like kilobyte order, not something unreasonable. And then the verification of the result is very, very cheap. It's only 3 pairing operations. The only overhead you get is basically if you were to have an extremely large circuit that I needed to run with a vast quantity of inputs, then yeah, the evaluation time for that circuit would be non-trivial. You want to consider probably some other method. Yeah. But I think it can be made practical so long as you have sufficiently small programs.
Okay, well, one more question.
I think a couple of slides forward, you had this animation that gives nice intuition into elliptic curves, and yeah. So could you just maybe try to explain again in very simple terms what is very difficult to compute? Why is it? What is computationally irreversible?
Okay, so this is the group exponentiation operation where I'm taking a point P and then performing this repeated exponentiation operation right here. So this is G raised to an integral power. To to recover so basically, if you want to think of it in dumbest terms, basically like you have this this billiard board of points. I put the ball at one point, I hit it with some force, it bounces off many, many times, and then lands at some point on the billiard board. To recover exactly where I shot the ball from, or what the exact force that I applied to get the end result state is actually quite difficult. And like I said before, you're doing this over this field of unimaginable size. So in the elliptic curve public key scheme, your public key is basically just the base point of the curve raised to a private number, which is some value between 0 and the field modulus, which is some unimaginably huge number. So it's quite trivial to do multiplication and addition operations in here. However, it's non-trivial to do the same number of inversions for these operations. Does that make sense?
Okay, let's thank the speaker again. So now if there are any project maintainers here who didn't do a presentation yesterday, you can get 2 minutes now to explain your project and ask if anyone wants to help you out with it. And if you do so, please queue up over there.